Hello, my name is Michal Zima, and I've prepared to talk about WrapSix, which is software I have programmed, and I'll tell you how you can build it and how you can use it. I'll talk about what WrapSix is and how this type of applications perform in real networks, and how you generally can optimize similar applications to have high performance. In the second part of my talk, I'll briefly introduce Net64 and DNS64 and generally tell you how you can get it running. So first, what WrapSix is, it's open source implementation of Net64. What Net64 is, I'll cover in the second part of my talk. Currently, it's important that it's specialized networking application and that it runs in user space. This has several impacts, such as what is in user space generally has lower performance than if it's in a kernel space. And WrapSix is an alternative to other Net64 software like Optimise or Tayga. But WrapSix performs much better than these two. And I'll tell you what's the trick. Before I started developing WrapSix, I said to myself that it would be fine that the WrapSix should be suitable for production environments. That means that it should be able to handle high traffic and at the same time cause minimal latency to it. When I talk about high-speed traffic or high throughput, it's worth thinking what this means. I can, as a programmer, think that 1 gigabit throughput, that seems to be fine. So, as a programmer, I test my program with 1.5 kilobyte packets, and I'll see that they come through and they come back, and I can be satisfied and tick it as done. But when it comes to real network, there are many smaller packets, and when we look at this comparison, for those 52 bytes packets, there is a huge difference. What amount of data the software should be able to handle. This is also kind of marketing from authors of network applications. I have an example here from Tayga's homepage, which says, Tayga is fast, can saturate gigabit Ethernet on a modest PC hardware. I can't say that it's not true, because it is, as you can see, but you can also see that it doesn't perform at such level on different packet sizes. And that's what you don't know until you install it into network. So the problem is how to maximize amount of process packets per second. If we need to process another, say, 2.4 million packets, then we find out that we call another 2 million routines which processes packets, and the kernel calls its internal routines as well. And that's quite a lot of code which has to run. One approach we can process more packets is to use more hardware. Typically, put more threads into the application and send and process few packets with one thread, another bunch of packets with the second thread, and so on. But you have to keep in mind that those threads are sharing the same state information of connections. So you have to handle those mutual exchanges, like not to come to inconsistent state between threads. Also, net64 requires preserving order of packets of the same flow. So it's not as easy as just putting some packets to some threads, but there should be some logic which controls this. A bit easier is it if we put only specific packets to specific threads. For example, one thread could process IPv4 data and another thread IPv6 data. This way it could be quite nicely done. And there is one more approach, the better one, I think. It's in optimizing the processing routines just to use less power to process a packet. This way, one can save power and don't have to go into the problems parallelizing brings. Especially if you optimize your code, you can't introduce race condition bugs. In parallelized software, they're quite common. And as opposed to parallelization, optimizing guarantees you higher performance. That doesn't seem logic on the first sight, but there are several things that comes in it, like sharing content of caches and such things that can slow the more threaded application. And of course, if we had optimized software, we can always go for more threads. So first step should be to clean the code from unused code, which is not very efficient, which doesn't do what is needed. Some redundancy in pre-computation can be eliminated, and it's worth optimizing jumps, because jumping causes performance hit as they break CPU pipeline. I won't explain what it is. Generally, in a if-else case, there is also jumping, and the first branch should be always the more probable one. So the CPU doesn't always jump to the code and doesn't slow your code. And also cycles are quite important in optimizing, because there is always something that could be done better. And another field you should consider is that memory is not as fast as you thought. Most programmers think that if they work with RAM, they're fine because they don't work with hard disk, which are really slow. But if you consider that existing RAM costs hundreds of CPU cycles and compare it to access to some level of cache, you find out that existing cache is much cheaper, and it's worth optimizing your code so that it first processes the data it has in cache, and if it has done, then move to another code, another data, which it can load from memory. I'll have one more thing at memory optimizing. It's a thing that dynamic allocation of memory is generally slower than static allocation, which is usually not considered when programming applications. And it's also worth mentioning that standard function to allocate memory, malloc, from standard C library is not the only available allocator. There are many others which are worth trying and comparing. Here you can see what difference it makes if you do 100 million allocations and some stuff. If you allocate statically or dynamically, it's 5 seconds, which is quite a lot. Because if we want to achieve performance of our application, which would be able to handle 2 million of packets, and we counted this result through packets, we'll find that we would need about 1/8 of a second just to allocate one piece of memory per packet, which is quite a lot. Because we usually don't do just one allocation per packet. Another important thing you should take into consideration when programming is choosing the right data structure, because choosing some bad would only slow you down. In the case of net64, there is usually the need to look up connections, fragments, or to check if there isn't any connection which should expire. There are several data structures you can choose from. The first, which is quite well known, is a hash table. It's quite popular because it's potentially very fast, but there are few disadvantages. To be really fast, it needs a good hash function which uniformly distributes the data among the memory space. And net64 very often needs to store many entries, sometimes just few, sometimes tens of thousands. So you can't really set up some hash table and just leave it as it is because of collisions. So you additionally need to implement some dynamic resizing. Or you can choose another data structure which I did choose. It's called Radix tree, and it's kind of those prefix trees, which in this case have fixed height, just based on the key length, which can be chunked and then used to access the deeper levels of the tree. I found very universal use in a Net 6.4, except one case. I use it for everything. It's also fast, and the advantage is that its speed doesn't change with stored entries. You can store 2 entries or 2 millions, and it still be the same fast. And one nice feature is that it allows partial lookups, how I call it, which is that you just take part of the key and look to a few levels and see if there is some other level or if there isn't any entry for that key. That's useful for looking if there is some connection for a specific IP address, for example. There is a scheme how Radix tree works. It's just a counter of entries in each node and an array statically allocated where in each field you store just a pointer to another node, and as index to each field you use chunk of the key. There is example of some data with key 0x, 02, 01, 01. So if we chunk it in 1 byte chunks, then just 3 steps are needed to access the data. Another data structure which is used in WrapSix is linked list, because it's much better to look at the beginning of the list, like the queue, if there is some connection which is to expire or not. And it's much faster than to traverse the whole tree and check, is there some connection which should expire, which timed out or not. I'm getting to another level of optimizations. It's tuning of operating system, because if you optimize your application, you will find out that your operating system is not your friend at all the time. So you have to optimize it as well. And there are things you can do without recompiling kernel and so on. It's like saying it to fix the CPU affinity of your application, so the application doesn't jump from one core to another and just sits on one. And if it is threaded application, you can put each thread on a separated core, so you better use the power you have. And it's also a good thing to set your application or each thread the highest priority, so the scheduler doesn't sleep it or put it away from the core. And quite nice optimization is in hardware, because if you have less threads than cores, you can disable hyperthreading because it doesn't give you any advantage. And you can also reduce number of CPUs. I'll explain it on an example. If your application is able to run on one CPU, for example, it has only 2 or 3 threads, and the CPU has 4 cores, you don't need the second CPU. But the operating system, to use the available power efficiently, it uses the second CPU to load packets from the network card and processes them on the second CPU and then send them to your application to the first CPU. So there's a huge performance hit. And if you remove the second CPU and force the kernel to use the same as uses your application, then sending packets just inside one CPU is much, much faster. To sum it up, I prepared a graph where you can see an unoptimized version of WrapSix and the version with optimizations I presented here. Here you can see that before it even couldn't handle 1 gigabit with the biggest packets. However, there is still a lot of work to be done for the smallest packets. So I'm not finished yet. You can remember that I've said that megabits are not as interesting as packet counts. So I have also comparison of all this. Before, it was able to handle just around 170,000 packets, and after it almost doubled to 300,000 packets, which is nice, but it's not the goal I have. Those 2 millions. There is still much to be done. So I'm moving to the second part. First of all, I should say what Net64 is and how it works. It basically is for connecting IPv6 networks to the internet, where are servers without IPv6 connectivity, and it behaves in this way. If we have a computer which doesn't have IPv4 connectivity and it wants to access example.com, it asks a DNS64 server for a DNS record, and the DNS64 asks ordinary DNS server, and if it says that such record doesn't exist, then DNS64 asks for ordinary A record, which is that one with IPv4 address. And from that address, it can make IPv6 address for the computer, so it can access the host it wants. So it sends a request to the address it received from DNS64, and it arrives to Net64 server, which translates the packet to IPv4 and sends it to to the real example.com host. The example.com doesn't know that the client is IPv6 only, so it normally replies, and net64 again translates the packets to IPv6 and returns the reply to the client. And this way the communication can proceed. So DNS64 is quite well implemented in bind server, and there exists also for unbound some patch, but it's not maintained, it's just for an old version. But if there is need, it can be used. Next thing is that bind can be very easily configured to behave as DNS64. It just needs to listen on IPv6 interface to do some recursion or forwarding, it depends. And it needs to know the NAT64 prefix, which is used in the network. So the packets the client will send can arrive to NAT64. Yeah, so it doesn't send it to some nonsense address. It's good to test it before it goes to production. So you can test it, for example, with Linux days, which doesn't have for a record. To get working net64, you can download WrapSix from its homepage, configure it. I'll show you in more details how it can be configured. And run typical triplet. Start it, and it's important to ensure that IPv6 forwarding is disabled on the system because it doesn't go well with WrapSix. Because I had different priorities than some nice configuration interface or configuration files, I just left it in source code, but in documented sections, so you can find it easily. You can configure the interface where the WrapSix will run. You should assign it an IPv6 address, but an unassigned one, so the operating system shouldn't know about it. Otherwise, the TCP won't work. Then you set up the net64 prefix and MTU on the IPv6 side. So if you know about some bottleneck in your network, you can set it there. If you test it, it works well. Just treat the host like normal host with IPv6, and WrapSix will translate it to the IPv4, and replies will be translated back. And basically, you won't recognize the difference between native IPv6 and translated one. So, thank you. Do you have any questions? So, thank you.